Close your eyes and let yourself drift away from Earth, away from the day, and into the infinite embrace of space. Out here, in the velvet darkness, time moves differently. A single day on Venus lasts longer than its entire year around the sun. Imagine that, the sun rising and setting just once while an entire orbit completes itself. As we float together through this cosmic ocean, know that you are made of stardust. Every atom in your body, except for hydrogen, was forged in the heart of a dying star billions of years ago. You are, quite literally, the universe experiencing itself. The moon, Earth's faithful companion, is slowly drifting away from us at about 3.8 centimeters per year. But don't worry, it will take millions of years before we notice any difference. For now, it hangs there, pulling gently at our oceans, creating the rhythm of tides that has lulled countless souls to sleep. Space itself is not completely silent, though no sound can travel through its vacuum. If it could, the sun would roar at us with the sound of 10 million earthly thunderstorms, constantly, endlessly. But instead, we receive only its light, taking 8 minutes and 20 seconds to reach us across 93 million miles. Let us drift closer to our star, our sun. This massive sphere of plasma is so large that 1.3 million Earths could fit inside it. Yet for all its grandeur, it is merely a middle-aged, medium-sized star, unremarkable among the 200 to 400 billion stars in our galaxy alone. The sun's core burns at 27 million degrees Fahrenheit, where hydrogen atoms fuse into helium, releasing the energy that warms your face on a summer day. But that energy, born in the core, takes between 10,000 to 170,000 years to reach the sun's surface, bouncing from atom to atom in an impossibly long journey. Every second, the sun converts 600 million tons of hydrogen into helium. In this process, 4 million tons of matter are converted into pure energy, following Einstein's famous equation. This has been happening for 4.6 billion years, and will continue for another 5 billion more. The sun's atmosphere, called the corona, is mysteriously hotter than its surface. The surface temperature is about 10,000 degrees Fahrenheit, but the corona blazes at millions of degrees. Scientists are still unraveling this paradox, this cosmic mystery hanging in plain sight. Solar wind streams from the sun constantly, a flow of charged particles traveling at 1,000,000 miles per hour. When these particles interact with Earth's magnetic field, they create the aurora borealis and aurora australis, curtains of light dancing in polar skies. The sun rotates, but not as one solid object. Its equator spins faster than its poles, completing a rotation in about 25 days, while the polar regions take up to 36 days. This differential rotation helps create the sun's complex magnetic field. Sunspots, those dark patches on the sun's surface, are actually cooler regions at around 6,500 degrees Fahrenheit. They appear dark only by contrast to the surrounding brilliance. These spots follow an 11-year cycle, waxing and waning in a solar heartbeat. One day, in about 5 billion years, the sun will exhaust its hydrogen fuel. It will swell into a red giant, possibly engulfing Mercury, Venus, and perhaps even Earth. But that day is unimaginably far away, rest easy. After its red giant phase, the sun will shed its outer layers, creating a planetary nebula of breathtaking beauty. Its core will remain as a white dwarf, slowly cooling over trillions of years. Let us drift inward now, toward Mercury, the smallest planet and closest to the sun. Despite its proximity to our star, Mercury is not the hottest planet. Its thin atmosphere cannot trap heat, so temperatures swing wildly from 800 degrees Fahrenheit in sunlight to minus 290 degrees at night. Mercury has the most eccentric orbit of all the planets, an elongated ellipse that brings it as close as 29 million miles to the sun and as far as 43 million miles away. Ancient astronomers thought Mercury was two different objects, one appearing in the morning sky, one in the evening. The planet is covered in craters, silent witnesses to billions of years of asteroid impacts. The largest, the Caloris Basin, is 960 miles across, created by an impact so powerful it caused shock waves that traveled around the entire planet. Mercury has a magnetic field, surprising for such a small world. Its iron core makes up 75% of the planet's radius, giving it the second highest density of any planet after Earth. Now we come to Venus, Earth's twin in size but utterly different in character. Shrouded in thick clouds of sulfuric acid, Venus hides a hellish surface where lead would melt and temperatures reach 900 degrees Fahrenheit. The atmospheric pressure on Venus is 92 times that of Earth, equivalent to being 3,000 feet underwater in Earth's oceans. This crushing pressure would flatten any visitor in moments. Venus rotates backwards compared to most planets, spinning clockwise when viewed from above. Scientists believe a massive collision in the distant past may have knocked it into this retrograde rotation. The planet's clouds are so reflective that Venus is the brightest natural object in our night sky after the moon. Ancient peoples called it both the morning star and evening star, not realizing it was a single world. Soviet Venera probes managed to land on Venus in the 1970s and 1980s, surviving for up to 2 hours before succumbing to the extreme conditions. They sent back the only photographs we have of Venus's surface. Lightning storms rage constantly in Venus's atmosphere, more frequent than on Earth, crackling through clouds of battery acid in an alien sky. Home now. Earth, our pale blue dot, the only world we know that harbors life. From space, Earth glows blue and white, swirled with clouds, 71% covered by oceans that make life possible. Earth is the densest planet in our solar system, with an iron-nickel core surrounded by a molten outer core that generates our protective magnetic field. This invisible shield deflects the solar wind, preventing it from stripping away our atmosphere. Our planet orbits the Sun at 67,000 miles per hour, hurtling through space while rotating at 1,000 miles per hour at the equator. Yet you feel none of this motion, cradled in gravity's gentle embrace. Earth's axis is tilted 23.5 degrees, giving us our seasons as different hemispheres lean toward or away from the Sun during our yearly journey. Without this tilt, there would be no spring, no autumn, no winter's rest or summer's warmth. The Moon, Earth's only natural satellite, is slowly but steadily moving away from us. Billions of years ago, it was much closer, and days were much shorter. Tides were enormous, crashing against ancient shores. The Moon is tidally locked to Earth, always showing us the same face. The far side, often called the dark side, receives just as much sunlight but remained hidden from human eyes until 1959. The Moon's gravity creates tidal forces that gradually slow Earth's rotation. Our days grow longer by about 1.7 milliseconds per century. Time itself is stretching, imperceptibly. The Moon was likely formed 4.5 billion years ago when a Mars-sized object called Theia collided with the early Earth. The debris from this cataclysmic impact coalesced into our lunar companion. Without the Moon, Earth's axial tilt would vary wildly over millions of years, making climate chaotic and perhaps preventing the stable conditions needed for complex life to evolve. The Moon's surface is covered in a fine dust called regolith, created by billions of years of micrometeorite impacts. Astronaut footprints left in 1969 will remain there for millions of years, undisturbed by wind or rain. Beyond Earth lies Mars, the red planet, colored by iron oxide rust covering its surface. From Earth, it glows in the night sky with a warm, reddish hue that captured human imagination for millennia. Mars has the largest volcano in the solar system, Olympus Mons, standing 72,000 feet high and 374 miles across. 3 times taller than Mount Everest, it formed over billions of years of eruptions. The planet also hosts Valles Marineris, a canyon system stretching 2,500 miles long, 125 miles wide, and up to 4 miles deep. If placed on Earth, it would span from New York to California. Mars has 2 small, irregularly shaped moons, Phobos and Deimos, likely captured asteroids. Phobos orbits so close and so fast that it rises and sets twice each Martian day. A day on Mars is remarkably similar to Earth's, lasting 24 hours and 37 minutes. Martian seasons exist too, though they last twice as long because Mars takes 687 Earth days to orbit the Sun. Mars once had liquid water flowing across its surface, carving channels and filling ancient seas. Much of that water is now locked in ice caps and frozen in the soil. The atmosphere on Mars is 95% carbon dioxide but incredibly thin, just 1% the pressure of Earth's atmosphere. You could not breathe it, and water would boil at room temperature. Dust storms on Mars can grow to planetary scale, enveloping the entire world in a reddish haze that lasts for months. These storms have challenged multiple Mars rovers throughout their missions. The Martian sky is a butterscotch color during the day due to dust suspended in a thin atmosphere. At sunset, however, the sky near the sun appears blue, the opposite of Earth. Mars has the longest dust devil tracks in the solar system, stretching for miles across the rusty plains, like the signatures of invisible giants wandering the desert. Between Mars and Jupiter lies the asteroid belt, a vast ring of rocky debris left over from the solar system's formation. Millions of asteroids orbit here, from tiny pebbles to dwarf planet Ceres, which is 590 miles in diameter. Despite popular depictions, the asteroid belt is mostly empty space. If you stood on one asteroid, you likely wouldn't be able to see another with the naked eye. They are separated by vast distances. Ceres contains about a third of the asteroid belt's total mass. It has a spherical shape and may harbor a subsurface ocean of liquid water beneath its icy crust. Many asteroids are rich in metals like iron, nickel, and even platinum. Some scientists estimate a single metallic asteroid could contain more platinum than has ever been mined on Earth. The asteroid belt failed to form a planet because Jupiter's immense gravity stirred the region too violently, preventing the material from coalescing into a single world. Now we approach Jupiter, king of planets, so massive that all other planets combined could fit inside it with room to spare. Jupiter contains more than twice the mass of all other planets together. This gas giant has no solid surface. Descending through its atmosphere, pressure and temperature increase until hydrogen becomes liquid metal. At the very center may lie a rocky core, but no one knows for certain. Jupiter's Great Red Spot is a storm that has raged for at least 400 years, possibly much longer. This anticyclonic storm is larger than Earth itself, with wind speeds exceeding 400 miles per hour. The planet rotates faster than any other in our solar system, completing a day in just under 10 hours. This rapid spin causes Jupiter to bulge noticeably at its equator. Jupiter has 95 known moons, a miniature solar system unto itself. The four largest, discovered by Galileo in 1610, are worlds in their own right. Europa, one of these Galilean moons, is covered in ice but likely harbors a global ocean beneath its frozen shell. This ocean may contain twice as much water as all of Earth's oceans combined. Io, another Galilean moon, is the most volcanically active body in the solar system. Tidal forces from Jupiter's gravity squeeze and stretch Io constantly, generating intense internal heat. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. It's the only moon known to have its own magnetic field. Callisto's surface is the oldest and most heavily cratered in the solar system, a battered record of 4 billion years of impacts. Jupiter's powerful magnetic field is 20,000 times stronger than Earth's, extending millions of miles into space and trapping intense radiation that would be lethal to humans. Beyond Jupiter glows Saturn, adorned with the most spectacular ring system in the solar system. These rings extend up to 175,000 miles from the planet but are incredibly thin, sometimes just 30 feet thick. Saturn's rings are composed of countless particles of ice and rock, ranging in size from grains of sand to house-sized chunks. They reflect sunlight brilliantly, making Saturn one of the most beautiful sights through a telescope. The rings are not solid structures but billions of individual pieces, each following its own orbit around Saturn. They formed either from a destroyed moon or from material that never coalesced into a moon. Saturn is the least dense planet in the solar system. If you could find an ocean large enough, Saturn would float, being less dense than water. Like Jupiter, Saturn is primarily hydrogen and helium, with no solid surface. Wind speeds in Saturn's atmosphere can reach 1,100 miles per hour, faster than Jupiter's storms. Saturn has 146 known moons, more than any other planet. The largest, Titan, is bigger than the planet Mercury and has a thick atmosphere. Titan is the only moon in the solar system with a substantial atmosphere, composed primarily of nitrogen like Earth's. Liquid methane and ethane form lakes and rivers on its surface. Enceladus, another of Saturn's moons, shoots enormous geysers of water ice into space from its south polar region. A subsurface ocean likely feeds these geysers. Saturn's hexagonal storm at its north pole is one of the strangest features in the solar system. This six-sided jet stream pattern is 20,000 miles wide and has persisted for decades. Every 15 years, as Saturn orbits the Sun, the angle of sunlight on the rings changes, and they appear to vanish when viewed edge-on from Earth. They're still there, just too thin to see. Far from the Sun's warmth lies Uranus, the ice giant tilted on its side. Its axis is tilted 98 degrees, meaning it essentially rolls around the Sun like a ball. Each pole gets 42 years of continuous sunlight, then 42 years of darkness. Uranus appears blue-green due to methane in its atmosphere, which absorbs red light. The planet's interior contains water, methane, and ammonia ices surrounding a small rocky core. Uranus has 13 faint rings and 27 known moons, most named after characters from Shakespeare's plays. The largest moon, Titania, is just 980 miles in diameter. The planet was the first discovered with a telescope, found by William Herschel in 1781. All planets visible to the naked eye had been known since ancient times. Scientists aren't certain what caused Uranus's extreme tilt, but most believe a massive collision with an Earth-sized object during the solar system's early days knocked it sideways. Neptune, the final planet, is an intense blue color, deeper than Uranus. This blue comes from methane in its atmosphere, but an unknown compound gives Neptune its richer hue. Neptune has the strongest winds in the solar system, with gusts reaching 1,500 miles per hour. The planet is surprisingly active for a world so distant from the Sun's energy. Neptune was discovered not by observation but by mathematics. Irregularities in Uranus's orbit led astronomers to calculate where another planet must be, and there they found Neptune in 1846. Neptune's largest moon, Triton, orbits backwards relative to the planet's rotation. This retrograde orbit suggests Triton was captured from the Kuiper belt beyond. Triton is slowly spiraling inward toward Neptune. In millions of years, it will be torn apart by tidal forces, potentially creating a ring system more spectacular than Saturn's. Beyond Neptune lies the Kuiper belt, a vast region of icy bodies including Pluto, once called the ninth planet but now classified as a dwarf planet. Pluto is smaller than Earth's moon, with a diameter of just 1,400 miles. Pluto has 5 known moons. The largest, Charon, is so large relative to Pluto that they orbit a point between them, making them almost a binary system. The Kuiper belt contains hundreds of thousands of objects, remnants from the solar system's formation 4.6 billion years ago, preserved in the deep freeze of space. Beyond the Kuiper belt lies the Oort cloud, a spherical shell of icy objects surrounding our solar system. It extends perhaps 1 light-year from the Sun, nearly a quarter of the distance to the nearest star. The Oort cloud may contain trillions of objects. When the Sun or passing stars disturb these objects gravitationally, some fall inward, becoming the long-period comets that occasionally graze our skies. The heliopause marks the boundary where the solar wind meets interstellar space. NASA's Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. Voyager 1 is now more than 15 billion miles from Earth, traveling at 38,000 miles per hour. Its radio signals take over 22 hours to reach us, traveling at the speed of light. Both Voyager spacecraft carry golden records with sounds and images of Earth, messages in bottles for any civilization that might find them in the distant future. Our solar system orbits the center of the Milky Way galaxy at 514,000 miles per hour, yet takes 230 million years to complete one galactic orbit. The last time we were at this spot, dinosaurs were just beginning to evolve. Our Sun is one of an estimated 200 to 400 billion stars in the Milky Way, which itself is just one of 2 trillion galaxies in the observable universe. The nearest star system to our Sun, Alpha Centauri, is 4.37 light-years away. Even traveling at the speed of Voyager 1, it would take 70,000 years to reach it. Light from the Andromeda Galaxy, our nearest large galactic neighbor, takes 2.5 million years to reach Earth. When you look at Andromeda, you see it as it was before humans existed. The universe is 13.8 billion years old, formed in the Big Bang from an infinitely dense point that exploded outward, creating space, time, matter, and energy in an instant. The universe is expanding, and that expansion is accelerating. Distant galaxies are receding from us faster and faster, driven by a mysterious force called dark energy. Dark energy makes up about 68% of the universe's energy content. Dark matter, another mysterious substance we cannot see but can detect gravitationally, comprises another 27%. Everything we can see, all the stars and galaxies, is just 5% of the universe. There are more stars in the universe than grains of sand on all of Earth's beaches, an incomprehensible number beyond human intuition. Despite space's vastness, atoms are mostly empty space. If an atom were the size of a cathedral, its nucleus would be the size of a fly. The cosmic microwave background radiation, light from 380,000 years after the Big Bang, fills all of space. It's the afterglow of creation itself, cooled by expansion to just 2.7 degrees above absolute zero. Time passes differently in strong gravitational fields. Astronauts on the International Space Station age slightly slower than people on Earth, though the difference is tiny, just milliseconds over a lifetime. Looking up at the night sky, you are looking back in time. Light takes time to travel, so every star you see is as it was years, decades, or centuries ago. The night sky is a window into the past. Deep in the cosmos exist objects so dense and strange they defy imagination. Black holes, formed when massive stars collapse, create gravity so intense that nothing, not even light, can escape once it crosses the event horizon. The nearest known black hole to Earth is about 1,600 light-years away, safely distant. It was discovered not by seeing it, but by observing its gravitational effects on a nearby visible star. At the center of our Milky Way galaxy sits a supermassive black hole called Sagittarius A*, with a mass 4 million times that of our Sun. Despite this enormous mass, it's surprisingly quiet, feeding gently on nearby gas. If you could somehow survive approaching a black hole, time dilation would cause strange effects. To a distant observer, you would appear to slow down and freeze at the event horizon, never quite crossing it. Inside a black hole lies the singularity, a point of infinite density where the laws of physics as we know them break down. What happens there remains one of science's greatest mysteries. Neutron stars are the collapsed cores of massive stars, so dense that a teaspoon of neutron star material would weigh 1 billion tons on Earth. They pack more mass than the Sun into a sphere just 12 miles across. Some neutron stars spin hundreds of times per second, beaming radiation like cosmic lighthouses. We call these pulsars, and their timing is so precise they rival atomic clocks. Magnetars are neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. A magnetar's magnetic field halfway to the moon would strip the data from every credit card on Earth. When two neutron stars collide, they create ripples in space-time called gravitational waves, stretching and squeezing space itself. These waves travel at the speed of light across the universe. Neutron star collisions also create heavy elements like gold and platinum through rapid neutron capture. Much of Earth's gold was forged in such cataclysmic mergers billions of years ago. Comets are ancient wanderers, dirty snowballs of ice and rock that formed in the outer solar system billions of years ago. When they approach the Sun, heat vaporizes their ice, creating spectacular tails. A comet's tail always points away from the Sun, pushed by solar wind and radiation pressure, not by the comet's direction of travel. Some comets sport two tails, one of dust and one of ionized gas. Halley's Comet returns every 75 to 76 years, last visiting in 1986 and due back in 2061. Records of its appearances stretch back over 2,000 years in Chinese astronomical texts. The Oort cloud comets can take millions of years to complete a single orbit. Some have orbital periods longer than humans have existed as a species. Every day, about 100 tons of dust and sand-sized particles from space drift down to Earth's surface. You've probably breathed in a few atoms that came from space. Meteor showers occur when Earth passes through debris trails left by comets. The particles burn up in our atmosphere at speeds up to 160,000 miles per hour, creating shooting stars. Most meteors are no larger than a grain of sand, yet they create bright streaks across the sky when they burn up 50 to 75 miles above Earth's surface. The largest meteorite ever found on Earth, the Hoba meteorite in Namibia, weighs about 60 tons and has never been moved from where it fell. It's composed mostly of iron and nickel. About 66 million years ago, an asteroid 6 miles wide struck Earth near what is now Mexico's Yucatan Peninsula, creating the Chicxulub crater and causing the extinction of the dinosaurs. Earth's atmosphere protects us from most space debris. Without it, our surface would be as heavily cratered as the moon's, a testament to billions of years of cosmic bombardment. Beyond our solar system, astronomers have discovered over 5,000 exoplanets orbiting other stars. The first confirmed detection came in 1992, opening a new chapter in astronomy. Many exoplanets are unlike anything in our solar system. Hot Jupiters orbit incredibly close to their stars, with years lasting just days and surface temperatures hot enough to vaporize metal. Some planets orbit 2 stars at once, like the fictional world of Tatooine. These circumlunar planets would have stunning double sunsets. Scientists have found planets made largely of diamond, planets where it rains glass sideways in 400-500 mile-per-hour winds, and planets darker than coal that absorb nearly all light hitting them. The exoplanet 55 Cancri is thought to be covered in graphite and diamond. Its surface temperature reaches 4,900 degrees Fahrenheit, hot enough to melt rock. TRAPPIST-1, a cool dwarf star 40 light-years away, hosts 7 Earth-sized planets, 3 of which orbit in a habitable zone where liquid water could exist. They're packed so tightly that standing on one planet, the others would appear larger than our moon. Rogue planets drift through the galaxy untethered to any star, ejected from their birth systems or formed in isolation. There may be billions of these lonely worlds wandering the darkness. The nearest potentially habitable exoplanet, Proxima Centauri b, orbits the closest star to our Sun. It's just 4.2 light-years away, though just means it would take our fastest spacecraft 80,000 years to reach it. Some planets orbit pulsars, bathed in deadly radiation. How they survived the supernova that created their star remains a puzzle. Water has been detected in the atmospheres of several exoplanets. Finding biosignatures, chemical signs of life, in an exoplanet's atmosphere remains one of astronomy's great goals. Light is both a wave and a particle, a duality that puzzled scientists for centuries. Photons, particles of light, have no mass yet carry energy and momentum. Light travels at 186,282 miles per second in a vacuum, the universe's ultimate speed limit. Nothing with mass can reach this speed, though light itself moves eternally at it. Different wavelengths of light carry different amounts of energy. Gamma rays, the shortest wavelengths, carry enough energy to damage DNA. Radio waves, the longest, carry very little. The visible light we see is just a tiny fraction of the electromagnetic spectrum. If the entire spectrum were a piano keyboard spanning 60 octaves, visible light would span less than 1 octave. Sunlight reaching Earth has already traveled for 8 minutes and 20 seconds. If the sun suddenly vanished, we'd have 8 more minutes of daylight before darkness fell. The sun produces more energy in 1 second than humanity has used in its entire existence. This energy comes from nuclear fusion, the same process being pursued for clean energy on Earth. Stars shine in different colors based on their temperature. Cool red stars burn at around 5,400 degrees Fahrenheit, while hot blue stars blaze at over 45,000 degrees. The most distant light we can see, the cosmic microwave background, has been traveling for 13.8 billion years. It started as visible in ultraviolet light but has been stretched by the universe's expansion into microwave wavelengths. Redshift occurs when objects move away from us, stretching light toward longer, redder wavelengths. This redshift revealed that the universe is expanding. Some galaxies are moving away from us faster than light, carried by the expansion of space itself. This doesn't violate relativity because space itself is expanding, not the galaxies moving through space. Supernovae, the explosive deaths of massive stars, can briefly outshine entire galaxies containing hundreds of billions of stars. They're among the most energetic events in the universe. When a star explodes as a supernova, it releases as much energy in a few seconds as our sun will produce over its entire 10 billion-year lifetime. Type Ia supernovae have consistent brightness, making them standard candles for measuring cosmic distances. They helped reveal that the universe's expansion is accelerating. Gamma-ray bursts are the most luminous events in the universe, releasing more energy in seconds than the sun will emit in its entire life. They're likely caused by the collapse of massive stars or collisions of neutron stars. A gamma-ray burst pointed directly at Earth from within our galaxy could potentially cause a mass extinction by stripping away the ozone layer. Fortunately, they're rare and randomly directed. Nebulae are vast clouds of gas and dust where new stars are born. The Eagle Nebula's pillars of creation are columns of gas and dust 7 light-years tall, nurseries for infant stars. Planetary nebulae form when dying sun-like stars shed their outer layers, creating beautiful shells of glowing gas. The name is misleading, they have nothing to do with planets. The Crab Nebula is the remnant of a supernova that exploded in 1054 CE, recorded by Chinese and Arab astronomers. Its central pulsar spins 30 times per second. Quasars are the bright centers of distant galaxies powered by supermassive black holes consuming matter. The most luminous quasars outshine all the stars in their host galaxies combined. The energy from quasars can be so intense that they blow away gas from their host galaxies, potentially shutting down star formation and shaping galactic evolution. Space and time are not separate but woven together into space-time, a four-dimensional fabric that can be warped by mass and energy. Einstein's theory of general relativity describes gravity not as a force but as the curvature of space-time. Massive objects create dips in this fabric, like bowling balls on a trampoline. GPS satellites must account for both special and general relativity. Time passes slightly faster in orbit due to weaker gravity, and this tiny difference would cause navigation errors of miles if not corrected. Astronauts on the International Space Station age about 0.007 seconds less per 6 months than people on Earth due to their high orbital speed and slightly weaker gravity. Near a black hole, time slows dramatically. In the movie Interstellar, 1 hour on a planet near a black hole equaled 7 years on Earth. This is theoretically possible, though extreme. The Big Bang didn't happen at a point in space, it happened everywhere simultaneously. Space itself expanded, carrying everything with it. There is no center to the universe. The observable universe is 93 billion light-years across, even though it's only 13.8 billion years old. This is because space itself has been expanding, stretching the distance light has traveled. Beyond the observable universe lies more universe we can never see. Light from those distant regions hasn't had time to reach us yet, and some never will due to accelerating expansion. In the far future, trillions of years from now, the universe's expansion will have carried distant galaxies so far away that beings in the Milky Way won't be able to see them. The night sky will grow darker. The universe might be infinite, extending forever in all directions. If so, there could be infinite copies of Earth, infinite versions of you, living infinite variations of your life. The building blocks of life, amino acids, have been found in meteorites, suggesting that life's ingredients are common throughout the cosmos. Extremophiles on Earth survive in boiling water, frozen Antarctic lakes, deep ocean trenches, and even in radioactive waste. Life is far hardier than once thought, expanding the possibilities for life elsewhere. Europa, Jupiter's moon, has more water than all of Earth's oceans. Its ice-covered ocean could harbor life around hydrothermal vents, much like those on Earth's ocean floors. Enceladus, Saturn's moon, shoots water geysers containing organic molecules into space. These plumes could contain evidence of microbial life in its subsurface ocean. Titan, Saturn's largest moon, has lakes of liquid methane and ethane. Some scientists speculate that exotic life could exist there based on different chemistry than Earth's water-based life. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy. Depending on the values used, estimates range from 1, us, to millions. The Fermi paradox asks, if intelligent life is common, where is everyone? The Great Silence suggests either life is rare, civilizations are short-lived, or they're not interested in contact. SETI, the search for extraterrestrial intelligence, has been listening for alien radio signals for decades. So far, the cosmos has remained silent, or at least, we haven't recognized the message. If intelligent aliens exist and are trying to contact us, they might be so different that we wouldn't recognize their signals as artificial. We're searching for what we know, but they might be beyond our imagination. The sheer distances between stars make interstellar communication challenging. A radio message to the nearest potentially habitable planet would take 4.2 years to arrive, and another 4.2 years for any reply. The Milky Way is a barred spiral galaxy, with a central bar of stars and spiral arms radiating outward. From above, it would look like a cosmic pinwheel about 100,000 light-years across. Our galaxy is part of the local group, containing about 80 galaxies including Andromeda and Triangulum. The local group itself spans about 10 million light-years. The Andromeda Galaxy and the Milky Way are approaching each other at about 250,000 miles per hour. In about 4.5 billion years, they will collide and merge into a larger elliptical galaxy. When galaxies collide, stars rarely actually hit each other because of the vast spaces between them. Instead, gravitational forces reshape the galaxies into new forms. The largest known galaxy, IC 1101, is about 6 million light-years across and contains 100 trillion stars. By comparison, the Milky Way is only 200 to 400 billion stars. Galaxies cluster together due to gravity, forming groups, clusters, and superclusters. The Milky Way's local group is part of the Virgo supercluster, which spans 110 million light-years. Between galaxy clusters lie vast cosmic voids, regions with very few galaxies spanning hundreds of millions of light-years. The universe is a foam-like structure, with galaxies concentrated in filaments and sheets. Dark matter holds galaxies and galaxy clusters together. Without it, galaxies would fly apart as they rotate. We can't see dark matter, but we see its gravitational effects. The cosmic web is the large-scale structure of the universe, with galaxies arranged along filaments of dark matter like beads on strings, surrounding enormous voids. The most distant galaxy ever observed, Jade's GSC 13-0, shows us light from when the universe was just 320 million years old. We see it as it was billions of years ago. Space isn't a perfect vacuum. Even in the emptiest regions between galaxies, there's about 1 atom per cubic meter, mostly hydrogen. In the vacuum of space, liquids boil at lower temperatures. Your blood wouldn't boil if exposed to space, but the water in your skin and tongue would vaporize immediately. Metal objects that touch in the vacuum of space can weld together through a process called cold welding, because there's no oxide layer to keep them apart. The cosmic microwave background radiation has a temperature of 2.7 Kelvin, just 2.7 degrees above absolute zero. It's the coldest natural thing in the universe. The coldest place ever measured was created in a laboratory on Earth, where scientists achieved temperatures just a fraction of a degree above absolute zero, colder than anywhere naturally occurring in space. Absolute zero, minus 459.67 degrees Fahrenheit, is theoretically the coldest possible temperature. At this point, atoms would have minimal motion, though quantum mechanics prevents them from stopping completely. The hottest temperature ever created on Earth was in the Large Hadron Collider, reaching 9.9 trillion degrees Fahrenheit, hotter than the core of any star and recreating conditions from microseconds after the Big Bang. White holes are theoretical opposites of black holes, spewing out matter and energy instead of consuming it. They're permitted by the equations of general relativity but have never been observed. Wormholes, theoretical tunnels through space-time, could potentially connect distant parts of the universe or even different times. However, they would require exotic matter with negative mass to remain stable. If you could fold a piece of paper 42 times, it would reach the moon. The exponential growth of doubling means that seemingly small repeated actions can lead to astronomical results. Every atom of oxygen in your lungs, carbon in your DNA, calcium in your bones, and iron in your blood was created inside stars that exploded before our sun was born. You are literally made of stardust. The atoms in your left hand likely came from a different star than the atoms in your right hand. You are an assembly of ancient stellar debris. Humans have existed for about 300,000 years, but the universe is 13.8 billion years old. If the universe's age were compressed into a single year, humans would appear in the last 15 minutes before midnight on December 31st. All of recorded human history would span about 30 seconds in that cosmic calendar. Everything humans have ever built, written, or achieved fits into half a minute of cosmic time. Despite space's vastness, we've sent spacecraft to every planet in our solar system and landed rovers on Mars. The Voyager spacecraft have entered interstellar space, carrying messages from Earth. The famous pale blue dot photograph, taken by Voyager 1 from 3.7 billion miles away, shows Earth as a tiny pixel suspended in a sunbeam. Carl Sagan called it home to everyone you love, everyone you've ever heard of. Light pollution has grown so severe that 1/3 of humanity cannot see the Milky Way from where they live. The night sky that inspired millennia of wonder is fading from view. In truly dark skies, you can see about 4,500 stars with the naked eye. Each one is a sun, potentially with its own family of planets. The universe may be infinite, but the part we can interact with is finite and getting smaller as expansion accelerates. Distant galaxies are slipping beyond our cosmic horizon forever. Yet despite the universe's incomprehensible scale and age, despite the trillions of galaxies and countless stars, you are here now, conscious and aware, able to contemplate it all. That itself is perhaps the most wondrous fact of all. Let us return to the stars themselves, those brilliant beacons scattered across the darkness. Stars are born in stellar nurseries, vast clouds of gas and dust called molecular clouds, where gravity slowly pulls matter together over millions of years. A star begins its life when the core of a collapsing cloud becomes dense and hot enough for nuclear fusion to ignite. This moment, when hydrogen first fuses into helium, marks a star's birth as it joins the main sequence. Most stars spend 90% of their lives on the main sequence, steadily fusing hydrogen into helium in their cores. Our sun has been doing this for 4.6 billion years and will continue for another 5 billion. The smallest stars, red dwarfs, burn their fuel so slowly they could shine for trillions of years. The universe isn't old enough yet for any red dwarf to have died of old age. The largest stars, blue supergiants, live fast and die young. A star 50 times the sun's mass might live only a few million years before exploding as a supernova. Stars come in a rainbow of colors that reveal their temperatures. The coolest are red, warming through orange and yellow like our sun, then white, and finally blue for the hottest stars. Brown dwarfs are failed stars, objects too small to sustain hydrogen fusion in their cores. They glow faintly with leftover heat from formation, slowly cooling over billions of years. Binary star systems, where two stars orbit each other, are extremely common. More than half of all stars have at least one stellar companion, locked in an eternal gravitational dance. In some binary systems, if one star expands into a red giant, it can transfer mass to its companion, rejuvenating the smaller star and extending its life in an exchange of stellar matter. Variable stars pulse and change brightness in regular patterns. Cepheid variables brighten and dim so predictably they serve as cosmic measuring sticks for determining distances across the universe. The Hubble Space Telescope, launched in 1990, orbits Earth every 95 minutes at an altitude of 340 miles. It has made over 1.5 million observations and transformed our understanding of the cosmos. Hubble's deep field images, capturing tiny patches of apparently empty sky, revealed thousands of galaxies and regions thought to be blank. Almost everywhere we look, the universe teems with galaxies. The James Webb Space Telescope, launched in 2021, observes an infrared light and can see through cosmic dust clouds to witness the birth of stars and peer back to the universe's first galaxies. Webb orbits the Sun at a special point called L2, about 1,000,000 miles from Earth, where it remains in a stable position relative to Earth and Sun, always in shadow to keep its instruments cold. The Hubble and Webb telescopes work together, with Hubble seeing visible and ultraviolet light while Webb sees infrared, giving us a more complete picture of cosmic phenomena. Ground-based telescopes have grown enormous. The largest, like the Grand Telescopio Canarias, have mirrors over 34 feet across, gathering vast amounts of light to see faint, distant objects. Adaptive optics on modern telescopes use lasers to create artificial stars in the upper atmosphere, then measure how Earth's turbulent air distorts this light and rapidly adjust mirrors to compensate. Radio telescopes listen to the universe at wavelengths invisible to human eyes. The Very Large Array in New Mexico combines 27 dishes to create images of radio-emitting cosmic objects. The Event Horizon Telescope is not a single telescope but a network of radio dishes around the globe working together. In 2019, it captured the first image of a black hole shadow. Future space missions plan to visit Europa to search for life, return samples from Mars, and send probes to the ice giants Uranus and Neptune, worlds we've visited only once. Dark matter makes up 27% of the universe's mass energy, yet we've never directly detected a dark matter particle. It interacts only through gravity, invisible yet essential to galactic structure. Galaxies rotate in ways that don't match the visible matter they contain. Either dark matter exists, providing the extra gravity needed, or our understanding of gravity itself is incomplete. Dark energy is even more mysterious than dark matter. Discovered through observations of distant supernovae, it's causing the universe's expansion to accelerate, pushing galaxies apart faster and faster. The cosmological constant, represented by the Greek letter lambda, was introduced by Einstein and later abandoned. Dark energy has revived it as the simplest explanation for accelerating expansion. The universe's fate depends on dark energy's behavior. If it remains constant, galaxies will drift apart forever in the Big Freeze. If it strengthens, space could tear apart in a big rip. Fast radio bursts are millisecond-long flashes of radio waves from distant galaxies. Discovered in 2007, their cause remained mysterious for years. Some appear to come from magnetars, but others have no clear explanation. The WOW signal, detected in 1977 by a SETI radio telescope, lasted 72 seconds and appeared to come from deep space. It has never been detected again, and its origin remains unknown. Tabby's star, officially KIC 846-2852, showed strange, irregular dimming that briefly sparked speculation about alien megastructures. The dimming is likely caused by dust, but it captured imaginations worldwide. Oumuamua, the first interstellar object detected passing through our solar system in 2017, had an elongated shape and unexpected acceleration that puzzled scientists. Its true nature remains debated. The universe appears to have matter but almost no antimatter. When matter and antimatter meet, they annihilate. Why does matter dominate? This asymmetry is one of physics' deepest puzzles. Immediately after the Big Bang, the universe contained only hydrogen, helium, and traces of lithium. Every other element was created later inside stars or during stellar explosions. Stellar nucleosynthesis, the fusion process inside stars, builds heavier elements from lighter ones. Small stars create elements up to carbon and oxygen. Massive stars forge elements all the way to iron. Iron is the endpoint of fusion in massive stars. Fusing iron consumes energy rather than releasing it, so when a massive star's core turns to iron, fusion stops and the star collapses, triggering a supernova. Elements heavier than iron are created during supernova explosions through rapid neutron capture. Gold, platinum, uranium, and other heavy elements come from these violent events. Cosmic rays are high-energy particles, mostly protons, that zip through space at nearly the speed of light. They come from supernovae and other violent events, and a few strike your body every second. The interstellar medium, the gas and dust between stars, contains complex organic molecules including amino acids and even sugar molecules. The ingredients of life drift through space. Space smells, according to astronauts who've experienced it on their spacesuits after spacewalks. They describe it as a metallic scent, like seared steak or welding fumes, from high-energy particles. The coldest known place in the universe is the Boomerang Nebula, a dying star's outflow that has cooled to just 1 degree above absolute zero through rapid expansion. Hot gas between galaxy clusters, the intracluster medium, glows with X-rays at temperatures of millions of degrees. This gas contains more ordinary matter than all the galaxy's stars combined. Dust grains in space, typically smaller than smoke particles, block visible light but allow infrared through. This is why infrared telescopes can peer into dusty star-forming regions hidden from optical view. Jupiter's moon Io is stretched and squeezed by tidal forces from Jupiter and other moons, generating enough heat to power over 400 active volcanoes. It's the most geologically active body in the solar system. Io's volcanoes can shoot sulfur plumes 250 miles into space. The moon's surface is covered in sulfur and sulfur dioxide frost, painted in yellows, reds, and whites like a cosmic pizza. Europa's ice shell may be 10 to 15 miles thick, floating on a global ocean that could be 40 to 100 miles deep. Tidal heating keeps this ocean liquid despite Europa's distance from the sun. Ganymede, Jupiter's largest moon, has its own magnetic field, the only moon in the solar system with one. It may have a layered ocean sandwiched between layers of ice at different pressures. Callisto is ancient and inactive, its surface dark and heavily cratered. It may have a subsurface ocean too, though unlike Europa's, Callisto's ocean likely has little contact with rock that could provide nutrients. Saturn's moon Titan has a thick atmosphere and weather patterns. Methane rain falls from orange skies, filling lakes and flowing in rivers, creating an alien water cycle based on hydrocarbons instead of water. Titan's surface features dunes of hydrocarbon sand blown by winds in the thick atmosphere. These dunes stretch for hundreds of miles across equatorial regions. Hyperion, another moon of Saturn, has an irregular, sponge-like shape and tumbles chaotically through space rather than keeping one face towards Saturn like most moons. Saturn's moon Mimas has an enormous impact crater called Herschel that makes it resemble the Death Star from Star Wars. The impact nearly shattered the small moon. Triton, Neptune's largest moon, orbits backwards and is slowly spiraling inward toward Neptune. In a few 100 million years, it will be torn apart by tidal forces, creating a spectacular ring system. The solar wind flows constantly from the sun, a stream of charged particles traveling at hundreds of miles per second. It shapes planetary magnetospheres and creates the heliopause where it meets interstellar space. Coronal mass ejections hurl billions of tons of plasma from the sun into space. When directed at Earth, they can disrupt satellites, power grids, and communications in events called geomagnetic storms. The Carrington event of 1859 was the most powerful geomagnetic storm ever recorded. Aurora were seen as far south as the Caribbean, and telegraph systems worldwide failed or gave operators shocks. If a Carrington-level event struck today, it could cause trillions of dollars in damage to our technology-dependent civilization, knocking out power grids and satellites for months or years. Cosmic rays from deep space constantly bombard Earth. Our magnetic field and atmosphere shield us, but astronauts in space receive much higher radiation doses, limiting time they can spend in orbit. The Van Allen radiation belts, rings of charged particles trapped by Earth's magnetic field, were discovered by America's first satellite, Explorer 1, in 1958. Astronauts must pass through them quickly to minimize radiation exposure. Jupiter's radiation environment is so intense that electronics near the planet require special shielding. The radiation around Jupiter is strong enough to give a person a lethal dose in minutes. Interstellar space is not empty but filled with a thin plasma, dust, cosmic rays, and magnetic fields. The local interstellar medium has a temperature of about 7,000 degrees Fahrenheit despite being so diffuse. Shock waves from supernovae compress interstellar gas, triggering the collapse of molecular clouds and potentially sparking new generations of star formation. Death feeds birth in the cosmic cycle. The Sun's magnetic field reverses every 11 years, with the north and south magnetic poles switching places. This flip is related to the sunspot cycle and changes in solar activity. 1 light year, the distance light travels in a year, equals nearly 6 trillion miles. The nearest star system is 4.2 light years away, which means about 25 trillion miles. If Earth were the size of a golf ball, the Sun would be a sphere 15 feet across, located 1,600 feet away. On this scale, the nearest star would be over 400 miles distant. The Milky Way galaxy is about 100,000 light-years across. Light from one side of the galaxy takes 100,000 years to reach the other side, traveling at 186,282 miles per second the entire way. The Andromeda galaxy is 2.5 million light-years away. When you look at Andromeda, you see it as it was 2.5 million years ago, before modern humans evolved. The Virgo cluster, a collection of over 1,000 galaxies, is about 65 million light-years away. The galaxies we see there show how the universe looked during the age of dinosaurs. The observable universe has a radius of about 46.5 billion light-years, even though the universe is only 13.8 billion years old. This is because space itself has been expanding, stretching the distance light has traveled. If you could travel at the speed of light, it would still take 100,000 years to cross the Milky Way, 2.5 million years to reach Andromeda, and billions of years to reach the edge of the observable universe. The cosmic light horizon represents the farthest we can see, limited by the universe's age and the speed of light. Beyond this horizon, light hasn't had time to reach us yet. Cosmic expansion means that some galaxies are receding from us faster than light, even though nothing can move through space faster than light. Space itself can expand at any rate. If you could somehow travel to the edge of the observable universe, you would not find a wall or boundary. Instead, you would see 46.5 billion light-years of universe in every direction around you. The cosmic microwave background is the oldest light in the universe, released 380,000 years after the Big Bang when the universe cooled enough for atoms to form and light to travel freely. Before the cosmic microwave background was released, the universe was opaque, a hot plasma where light couldn't travel far before hitting a particle. The CMB marks the moment the universe became transparent. Tiny temperature fluctuations in the cosmic microwave background, just a few millionths of a degree, were the seeds from which all structure in the universe grew through gravity. The cosmic microwave background has a nearly perfect blackbody spectrum, exactly matching theoretical predictions. Its existence is one of the strongest pieces of evidence for the Big Bang theory. The dark ages of the universe lasted from 380,000 years after the Big Bang until the first stars ignited about 100 million years later. During this time, the universe was dark, filled with neutral hydrogen. The first stars, population 3 stars, were massive and short-lived, containing only hydrogen and helium. They exploded quickly, scattering the first heavy elements into space. Reionization occurred when the first stars and galaxies produced enough ultraviolet light to ionize neutral hydrogen throughout the universe, making it transparent again to ultraviolet light. The oldest known galaxy observed, GNZ 11, shows us light from when the universe was just 400 million years old, a mere 3% of its current age. Ancient quasars tell us that supermassive black holes with billions of solar masses existed when the universe was less than 1 billion years old. How they grew so large so quickly remains a mystery. The universe has been expanding for 13.8 billion years, but due to the expansion of space, objects we see at the cosmic horizon are now 46.5 billion light-years away. HD 189733b is a deep blue exoplanet, but not because of water. Its color comes from silicate particles in the atmosphere that scatter blue light, and it rains glass sideways in 400-mile-per-hour winds. Kepler 452b, sometimes called Earth's cousin, orbits a sun-like star in the habitable zone. It's about 60% larger than Earth and receives similar sunlight, though it's 1,400 light-years away. WASP 12b is being devoured by its star, stretched into an egg shape by tidal forces. Material from the planet streams toward the star, and the planet will be completely consumed in about 10 million years. Gliese 436b is an ice planet where water remains frozen despite temperatures of 800 degrees Fahrenheit. The planet's gravity is so strong it compresses water into exotic forms of ice. PSRJ 1719-1438b is a planet made of diamond, the compressed remnant of a star that once orbited the pulsar. It's about 5 times Earth's diameter, made of crystallized carbon. Trace 2b is the darkest known exoplanet, reflecting less than 1% of light that hits it. Darker than coal or acrylic paint, it absorbs nearly all light, though scientists aren't sure why. KELT 9b is the hottest known exoplanet, with dayside temperatures exceeding 7,800 degrees Fahrenheit, hotter than many stars. Molecules in its atmosphere are torn apart by the heat. Kepler 16b orbits 2 stars, like Star Wars Tatooine. From its surface, 2 suns would rise and set, casting double shadows and creating unique patterns of day and night. HAT P1b is one of the least dense planets known, with a density less than Cork. This puffy hot Jupiter is so bloated by heat that it would float in water if you could find an ocean large enough. 55 Cancri has such extreme temperature differences between its day and night sides that some scientists speculate it might have lava flows on the surface, flowing from the hot day side to the cooler night side. Yuri Gagarin became the first human in space on April 12, 1961, orbiting Earth once in his Vostok 1 capsule. His flight lasted 108 minutes and changed humanity's relationship with the cosmos forever. The Moon is the farthest humans have ever traveled from Earth. 12 people walked on the lunar surface between 1969 and 1972, a feat not repeated in over 5 decades. The International Space Station has been continuously inhabited since November 2, 2000. It orbits Earth every 90 minutes at 17,500 miles per hour, circling the globe 16 times per day. Astronauts on the ISS experience 16 sunrises and sunsets every 24 hours. To maintain a normal day-night cycle, they follow Greenwich Mean Time and use blackout shades. In microgravity, astronauts grow about 2 inches taller as their spines decompress. They shrink back to normal height after returning to Earth and readjusting to gravity. Without gravity's constant pull, astronauts' bones lose density and muscles atrophy. They must exercise about 2 hours daily to maintain bone and muscle mass during long missions. The farthest humans have traveled from Earth is 248,655 miles, achieved by the Apollo 13 crew as they swung around the Moon during their troubled mission in 1970. Water behaves strangely in microgravity, forming floating spheres held together by surface tension. Astronauts drink from pouches or special cups designed to use capillary action. Flames burn differently in microgravity, forming spherical shapes instead of the teardrop shapes we see on Earth. This is because hot gases don't rise without gravity to create buoyancy. Over 600 people from more than 40 countries have traveled to space. Yet this is just a tiny fraction of humanity, a reminder of how rare and precious the spacefaring experience remains. Space and time are not separate entities but interwoven into a single fabric called space-time. Every event in the universe exists at a specific point in this four-dimensional tapestry. Einstein showed that massive objects curve space-time around them, like a bowling ball placed on a stretched rubber sheet. We experience this curvature as gravity, not as a force but as the natural path through bent space. Time dilation means that time passes at different rates depending on velocity and gravity. A clock on a mountaintop ticks slightly faster than one at sea level because gravity is marginally weaker higher up. The twin paradox demonstrates time dilation dramatically. If one twin travels at near light speed while the other stays on Earth, the traveling twin ages more slowly and returns younger than their sibling. Gravitational waves, ripples in spacetime itself, were predicted by Einstein in 1916 but not directly detected until 2015 when LIGO observed waves from colliding black holes 1.3 billion light-years away. When gravitational waves pass through you, they stretch and compress space itself, though by amounts smaller than an atomic nucleus. You've been stretched and squeezed by gravitational waves many times without ever noticing. The speed of light is not just a speed limit for matter but the speed at which causality itself propagates through the universe. Nothing can carry information faster than light. If the sun suddenly vanished, Earth would continue orbiting for 8 minutes before the loss of gravity reached us, the same time it takes light to travel from sun to Earth. Quantum mechanics reveals that particles can exist in multiple states simultaneously until observed, a phenomenon called superposition. Reality at the smallest scales is probabilistic, not deterministic. Quantum entanglement allows particles to remain connected across vast distances. Measuring one instantly affects the other, no matter how far apart they are, though this cannot transmit information faster than light. Wolf-Rayet stars are massive, hot stars nearing the end of their lives, blowing away their outer layers in powerful stellar winds. They lose the mass of Earth every 1,000 years. These stellar winds travel at millions of miles per hour, enriching the interstellar medium with heavy elements forged in the star's core during its brief, brilliant life. Luminous blue variables are massive, unstable stars that vary in brightness unpredictably. Eta Carinae, the most famous example, became the second brightest star in the sky in the 1840s before fading. Eta Carinae ejected more mass than our entire sun during its 1840s outburst, creating a beautiful double-lobed nebula. It could explode as a supernova at any time, or in another 100,000 years. Thorn-Zitko objects are theoretical hybrid stars with a neutron star at the center surrounded by a normal stellar envelope. Only a handful of candidates have been identified. Zombie stars, or type IAX supernovae, are failed supernovae where the star survives the explosion, though heavily damaged. These walk among the living as stellar remnants that should have died. The Pistol star, one of the most luminous stars known, shines with the power of 10 million suns. Despite this, it's invisible to the naked eye, hidden by dust 25,000 light-years away. Hypervelocity stars travel fast enough to escape the Milky Way's gravity, ejected by interactions with the supermassive black hole at the galactic center or by supernova explosions in binary systems. T Tauri stars are young, variable stars still in the process of contracting before reaching the main sequence. Our sun was once a T Tauri star 4.6 billion years ago. Herbig-Haro objects are small patches of nebulosity formed when jets from newborn stars collide with nearby gas and dust, creating beautiful, glowing shock waves in stellar nurseries. Galaxy collisions are majestic, slow-motion events unfolding over hundreds of millions of years. Despite containing billions of stars, actual stellar collisions are rare due to the vast distances between stars. The antennae galaxies are two spiral galaxies currently colliding 45 million light-years away. Long tidal tails of stars stretch from both galaxies, resembling insect antennae reaching into space. When galaxies collide, their shapes are dramatically transformed. Spiral galaxies can merge to form elliptical galaxies, while gas clouds collide and trigger massive bursts of star formation. The Milky Way has consumed dozens of smaller galaxies throughout its history. The stars from these galactic meals now orbit within our galaxy, identifiable by their unusual orbits and compositions. In about 4.5 billion years, the Andromeda Galaxy will collide with the Milky Way. Computer simulations show the two will merge over billions of years, forming a giant elliptical galaxy nicknamed Milkomeda. During the Milky Way-Andromeda collision, Earth and our solar system will likely survive intact, though we might be flung into a different part of the merged galaxy or even ejected into intergalactic space. The night sky during the collision will be spectacular, with Andromeda appearing enormous and bright, and new stars forming in vast clouds of colliding gas, creating a celestial fireworks display lasting millions of years. Compact galaxy groups like Stephan's quintet show galaxies locked in gravitational combat, pulling streams of stars and gas from each other in a complex dance of destruction and creation. Head-on galaxy collisions can create ring galaxies, where a smaller galaxy punches through a larger disk galaxy, creating an expanding ring of star formation like ripples on a cosmic pond. Ultra-compact dwarf galaxies are the dense cores of galaxies that have been stripped of their outer stars by collisions, leaving behind small but incredibly dense stellar systems. Planet 9, a hypothetical planet, may lurk in the outer solar system beyond Neptune. Its existence is inferred from the unusual orbits of distant Kuiper Belt objects, though it has never been observed. If Planet 9 exists, it might be 5 to 10 times Earth's mass, orbiting at 400 to 800 times Earth's distance from the Sun, taking 10,000 to 20,000 years to complete one orbit. The frost line in our solar system marks the distance from the Sun where it's cold enough for water ice to form. This boundary, about 3 astronomical units from the Sun, determined which planets became rocky and which became gas giants. The late heavy bombardment occurred about 3.9 billion years ago when a sudden increase in asteroid and comet impacts pummeled the inner solar system, possibly triggered by Jupiter and Saturn shifting their orbits. Earth's moon stabilizes our axial tilt, preventing it from varying wildly over millions of years. Without the moon, Earth's tilt could vary from 0 to 85 degrees, causing dramatic climate chaos. Theia, the Mars-sized object that struck Earth 4.5 billion years ago to create the moon, may have contributed most of the water now in Earth's oceans, delivered during that cataclysmic collision. Saturn's rings are surprisingly young, possibly only 10 to 100 million years old, formed from a destroyed moon or captured comet. They're slowly raining down onto Saturn and may disappear in another 100 million years. The Cassini spacecraft, which studied Saturn for 13 years, deliberately plunged into Saturn's atmosphere in 2017 to avoid any chance of contaminating potentially habitable moons like Enceladus with Earth microbes. Jupiter acts as a cosmic shield for Earth, its massive gravity deflecting many asteroids and comets that might otherwise strike our planet. Without Jupiter, Earth might have suffered far more catastrophic impacts. The asteroid belt contains less mass than our moon. If all asteroids were combined into a single object, it would be smaller than our moon, despite Hollywood's depiction of densely packed rock fields. Neutrinos are nearly massless particles that barely interact with matter. Trillions pass through your body every second, mostly from the Sun, traveling through Earth as if it weren't there. A neutrino could pass through a light year of lead and have only a 50% chance of hitting a single atom. They're ghostly particles that flood the universe, carrying information from cosmic events. When supernova 1987A exploded, neutrinos from the blast reached Earth 3 hours before the light did. They traveled straight through the star's collapsing core while light had to work its way out through layers of stellar material. Muons are particles created when cosmic rays strike Earth's upper atmosphere. They should decay before reaching the ground, but time dilation at their high speeds allows them to survive long enough to be detected at sea level. The solar neutrino problem puzzled scientists for decades. Detectors found only 1/3 the expected neutrinos from the Sun. The solution: neutrinos change type as they travel, oscillating between 3 different varieties. Cosmic ray particles with energies exceeding anything achievable in human-made accelerators strike Earth's atmosphere regularly. The most energetic one detected, the oh my god particle, carried the energy of a baseball thrown at 60 miles per hour in a single atomic nucleus. The Cherenkov radiation glow occurs when particles travel faster than light can in a particular medium. Nuclear reactors glow blue from Cherenkov radiation as particles exceed light speed in water. Positrons, the antimatter version of electrons, are created in particle physics experiments and by some radioactive decay. When a positron meets an electron, both annihilate in a flash of gamma rays. Hawking radiation is theoretical radiation emitted by black holes due to quantum effects near the event horizon. Over unimaginably long timescales, this radiation causes black holes to evaporate completely. The quantum vacuum isn't truly empty but seethes with virtual particles that pop into existence and annihilate in tiny fractions of a second, a consequence of Heisenberg's uncertainty principle. The surface of Venus is hot enough to melt lead, with temperatures around 900 degrees Fahrenheit. This heat is maintained by a runaway greenhouse effect in its thick carbon dioxide atmosphere. Venus's atmospheric pressure would crush a human instantly. At 92 times Earth's pressure, it's equivalent to being nearly a mile underwater in Earth's oceans. The clouds of Venus contain sulfuric acid droplets. Rain from these clouds never reaches the surface, evaporating in the scorching heat of the lower atmosphere. Jupiter's Great Red Spot, though shrinking, is still large enough to swallow 2 Earths. This storm has raged continuously for at least 400 years, powered by Jupiter's internal heat. The winds in Saturn's northern jet stream reach 1,100 miles per hour, faster than the speed of sound on Earth. These winds encircle the planet in narrow bands, driven by the planet's rapid rotation and internal heat. Io's surface is constantly being resurfaced by volcanic activity. It has no impact craters because volcanic flows bury them faster than new impacts can create them. Titan's surface temperature hovers around -290 degrees Fahrenheit, cold enough for methane and ethane to exist as liquids while water ice is as hard as rock. The day-night temperatures swing on Mercury ranges over 1,000 degrees Fahrenheit, from 800 degrees in sunlight to -290 in shadow, the most extreme in the solar system. Enceladus's geysers shoot water 250 miles into space from cracks in its south polar region. Some of this water escapes entirely, while the rest falls back as snow. Mars's atmosphere is so thin that liquid water cannot exist on the surface. Water either boils away or freezes solid, with no liquid phase possible at current conditions. Atoms are 99.99999999999% empty space. If an atom were expanded to the size of a football stadium, its nucleus would be the size of a pea at the center. Despite being mostly empty, you cannot pass your hand through a table because of electromagnetic forces between atoms. These forces create the sensation of solidity from emptiness. Every breath you take contains atoms breathed by every person who has ever lived. In your lungs right now are atoms that were once breathed by Caesar, Cleopatra, and every historical figure. Your body contains about 7 octillion atoms, 7 followed by 27 zeros. Nearly all of them were created in stars and supernova explosions, then recycled through multiple generations of stars. The atoms in your body are constantly being replaced. Within about 7 years, almost every atom in your body will have been exchanged with atoms from the environment. Hydrogen, the simplest and most abundant element, makes up about 75% of the universe's ordinary matter. Your body is about 10% hydrogen by mass, mostly in water molecules. Carbon, the basis of all known life, is forged in stars through the triple alpha process where 3 helium nuclei fuse together. This process requires precise conditions to occur. Silicon, abundant in Earth's crust, could theoretically form the basis for alternative biochemistry, though carbon's versatility makes it far superior for creating complex molecules. Strange matter is a hypothetical form of matter that could be more stable than normal matter. If it exists, a single strange matter particle touching normal matter could convert it in a chain reaction. Degenerate matter in white dwarfs is so dense that a teaspoon would weigh about 15 tons. Electrons are pressed so close together that quantum mechanics prevents further compression. Over 8,000 satellites orbit Earth, though only about 4,000 are currently operational. The rest are space junk, defunct satellites still circling the planet. The International Space Station is the most expensive object ever built, costing over $150 billion and requiring cooperation among 15 nations over decades of construction. Voyager 1's golden record contains sounds and images of Earth, including greetings in 55 languages, music from various cultures, and sounds of nature. It will outlast human civilization, drifting through space for billions of years. The Hubble Space Telescope was launched with a flawed mirror, a manufacturing error that blurred its images. Astronauts installed corrective optics in 1993, restoring Hubble to perfect vision. Mars rovers Spirit and Opportunity were designed for 90-day missions but lasted years beyond their planned lifetimes. Opportunity operated for 15 years, traveling 28 miles across Martian terrain. The Juno spacecraft orbits Jupiter in a highly elliptical orbit, swooping close to the planet to study its interior, then swinging far out to reduce radiation exposure to its instruments. New Horizons flew past Pluto in 2015 after a 9-year journey, revealing Pluto's heart-shaped glacier and complex geology. It then continued to explore Kuiper Belt object Arrokoth. The Parker Solar Probe is humanity's closest approach to the Sun, diving through the corona at speeds exceeding 430,000 miles per hour, fast enough to fly from New York to Tokyo in under a minute. Parker's solar probe's heat shield withstands temperatures exceeding 2,500 degrees Fahrenheit while keeping instruments at room temperature just inches behind the shield. The Curiosity rover on Mars is nuclear-powered, using plutonium-238's radioactive decay to generate heat and electricity, allowing it to operate through Martian winter and at night. The universe is 13.8 billion years old. If compressed into a single year, the solar system formed in early September, life on Earth appeared in late September, and humans evolved in the last hour of December 31st. Complex multicellular life didn't appear on Earth until about 600 million years ago, despite life existing for over 3 billion years before that. Single-celled organisms dominated Earth for most of its history. The Sun is about halfway through its main sequence lifetime. It has burned for 4.6 billion years and will continue for another 5 billion before swelling into a red giant. When the Sun becomes a red giant, it will engulf Mercury and Venus, and possibly Earth. The oceans will boil away long before then, making Earth uninhabitable in about 1 billion years. After its red giant phase, the Sun will shed its outer layers as a planetary nebula, leaving behind a white dwarf about the size of Earth but with half the Sun's current mass. White dwarfs cool slowly over trillions of years, eventually becoming black dwarfs, cold dark stellar remnants. The universe isn't old enough yet for any black dwarfs to exist. Stellar remnants will dominate the universe's far future. In 100 trillion years, star formation will cease as galaxies exhaust their gas, leaving only dead stars, planets, and black holes. Black holes will be the last objects to evaporate through Hawking radiation. The largest will take 10 to the power of 100 years to disappear completely, a Google years, a timescale that makes the current age of the universe seem instantaneous. Protons, once thought eternal, may decay with a half-life longer than 10 to the power of 34 years. If so, even matter itself will eventually disappear, leaving only energy in an ever-expanding universe. The heat death of the universe, or Big Freeze, is the likely ultimate fate. The universe continues expanding, cooling toward absolute zero, all stars dead, all matter decayed, only darkness and cold remaining. The pillars of creation in the Eagle Nebula are about 5 light-years tall, columns of gas and dust where new stars are forming. The image from Hubble is one of astronomy's most iconic photographs. The Horsehead Nebula is a dark cloud of dust silhouetted against glowing hydrogen gas. It's about 1,500 light-years away and will dissipate in a few million years. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is the closest massive star-forming region to Earth at about 1,350 light-years away. Globular clusters are spherical collections of hundreds of thousands of ancient stars, orbiting galaxies like satellites. They contain some of the oldest stars in the universe. The Pleiades, or Seven Sisters, is a young star cluster just 100 million years old. Its brightest stars are hot, blue, and wrapped in reflection nebulae from dust in the region. Barnard Star is the nearest single star to our Sun at just 6 light-years away, though it's too faint to see without a telescope. It moves across our sky faster than any other star. Betelgeuse, the red supergiant in Orion, is so large that if placed at our Sun's position, it would extend past Mars's orbit. It will explode as a supernova someday, possibly within the next 100,000 years. When Betelgeuse explodes, it will briefly shine as bright as the full moon, visible even during daytime. After a few months, it will fade, leaving a beautiful expanding nebula. The North Star, Polaris, appears stationary because it lies nearly on Earth's rotational axis. But Earth's axis precesses slowly, and in 12,000 years, Vega will be the North Star instead. Binary star systems can produce beautiful astronomical phenomena. Algol, the demon star, appears to wink every 2.87 days as a dim companion star eclipses the brighter primary star. And so we complete our journey through 400 facts about space, having traveled from our Sun to the farthest reaches we can imagine, from the smallest particles to the largest cosmic structures. We've witnessed stars being born and dying, galaxies colliding across billions of years, planets of diamond and darkness, moons with underground oceans, and mysteries that still perplex the brightest minds. Through it all, one truth remains: you are part of this cosmic story. The iron in your blood was forged in a dying star. The calcium in your bones was created in a supernova. The oxygen you breathe with each gentle breath came from stellar fusion. You orbit a star at this very moment, one of hundreds of billions in a galaxy that is itself one of trillions. You spin through space on a world that hangs in a sunbeam, precious and rare, the only home we've ever known. The universe is vast beyond comprehension, ancient beyond imagining, strange beyond all expectation. Yet here you are, conscious and aware, able to contemplate infinity while lying comfortably in your bed. From the cosmic microwave background to the deepest darkness between galaxy superclusters, from quantum foam to the event horizons of black holes, the universe unfolds in majesty and mystery. Tonight, as you drift towards sleep, you travel through space on your planetary vessel, protected by a thin blanket of atmosphere, warmed by the light of an ordinary star, held gently by gravity's embrace. The stars will continue shining. Galaxies will keep spinning through the void. Somewhere, a star is being born. Somewhere else, one winks out of existence. The cosmic dance continues, eternal and serene. And you are stardust, you are cosmic, you are the universe itself, awakened and aware, if only for this brief and precious moment. Rest now in this knowledge. Let the vastness bring you peace. Let the eternal rhythms slow your thoughts. Let yourself drift on the tides of space-time itself, gentle and free. The universe embraces you. You are home among the stars. Sleep well, beautiful cosmic traveler. Dream of infinity.